Okay, well, thank you very much for that kind introduction, Dick. And thank you all for being here. It's really a great honor and pleasure to be back in Toronto for this event, and of course to be back in the province where I was born. I was born just about an hour away from here. I'm also really grateful to the Fields Institute for putting this together and for giving me this opportunity to talk about what we all do at the Fields Institute and to talk a little bit about what really motivates us in our work as mathematicians. I always loved numbers since I was, it's as far back as I can remember. And seeing patterns in numbers always excited me and is what really brought me into mathematics. Patterns in numbers as well as patterns in nature, patterns that I saw around me. I always started to ask questions about, why were those patterns there? And that was another way that I got into mathematics. And so it's a real pleasure to be able to share some of those little stories that brought me into mathematics, in the hope that it may inspire some young people here or the parents of young people who may encourage their children to go into mathematics, even if they're not just interested in science, but they're also interested in art. Because for me, I really feel like I got interested in mathematics through the art of patterns. So that's what I'd love to try and do today. So for me, mathematics really is the study of patterns. So from my point of view, mathematics is in large part the search for patterns, but not just the search for patterns, but also the search for explanations as to why those patterns are there. Because oftentimes, until you understand the patterns are there, they may not actually be there. Sometimes they're sort of false starts that make it seem like there's a pattern. And to know that that pattern really persists forever, you have to understand why it's there. And so that's what I feel mathematics is, in large part, and that's what mathematicians do. Such explanations, when you find them, even though they're just for that pattern that you just happen to see near you, when you find such explanations, those patterns and the explanation of those patterns can be used in other applications very often, beyond the context in which those patterns and those explanations were discovered. And some of the greatest discoveries in mathematics and in science, the most applicable mathematics, happened because people were just looking from the aesthetic point of view, looking for beauty. But then they had applications that really moved humanity forward and moved science forward. So examples of that are, people since ancient times have been looking at the planets and trying to understand what the patterns are in the motion of the planets. And eventually, with Newton and Kepler, but of course many others over the centuries, built up a theory that explained those patterns in the sky. That led to the theory of gravitation. And of course, that's extremely important in our everyday lives. It's allowed us to launch our own satellites, and we can understand where those satellites go because we understand the theory of gravitation. Another place where just looking for patterns for the sake of the art of it is in the area of genomics. Understanding that DNA had a double helix structure, and its composition, understanding the patterns in those genomes are now helping us in curing disease, but when it started out, it was just trying to understand patterns in our genomes. So there are many, many examples of this throughout history where discoveries were made just by searching for beauty in our lives and in the world around us, but it's ended up having tremendous applications throughout science and throughout humanity. So that's what mathematicians try to do. They're really not looking at the application so much, but when looking for beauty and trying to understand it, it ends up often transforming neighboring areas, neighboring sciences, and neighboring applications that were initially completely unexpected. Okay, but mathematicians look for patterns. For number theorists, which is what I do, I'm a number theorist, and much of what the field's symposium is this week, is a number theory symposium this year. And for us, our natural world, well, we have our usual natural world around us, but we have another natural world, which is the universe of numbers, the universe of whole numbers. So what are the whole numbers? They're just the numbers that we count with, 0, 1, 2, 3, 4, and so on. But also the negative numbers, -1, -2, -3, and so on. Those are the whole numbers. And that, in some sense, is our universe. And we look for patterns in just this universe here. Sometimes this universe gets a little bigger, but eventually number theorists claim that their main interest is understanding this universe, just here. And so number theory is the branch of mathematics that studies patterns in the whole numbers, in this universe of ours. And so just to give you the most basic example of patterns that occur in the whole numbers, well, number sequences are perhaps the most basic types of patterns that mathematicians study. So a number sequence is just a sequence of numbers. And I can give you some examples that you've probably all seen, and then you'll understand why, what the patterns are and why we're interested in them. I'll start out with the easiest possible sequence. Everyone see the pattern? Anyone know the next term? Okay, that's called the all-one sequence. It may look very trivial, but it actually ends up being useful a lot. Okay, we'll get a little bit harder now. Not much. Okay, so these are just our counting numbers, 1, 2, 3, 4, and so on. So these are the two basic patterns from which it all begins. Okay, everyone see the pattern here? What are these called? The odd numbers. And it has a complement, which are called the even numbers. Okay, and these are some of the patterns that will come up in this talk, so I just want to make sure that everybody knows their names when I say them. These ones were all easy. All right, what are these? 1, 4, 9. Very good. Yeah, these are the square numbers. These are the cubes. So each of these sequences is kind of slightly going faster than the previous one. What are these called? Powers of 2. That's right. If you take every other element in that sequence, what's the next term? 4096. That's right. What are these called? Powers of 4. That's right. So in these examples, the first 4 of these were basically sequences that exhibit linear growth. Okay? There's just a constant amount. They're growing a constant amount each time. Whereas the next 2 sequences, these exhibit what are called polynomial growth. Okay? It's growing as a power. If you look at the nth term, it's growing as a power of that, the second power or the third power. But then these last two sequences here, these are growing faster than either of those. They're not growing, if you look at the nth term, they're growing faster than any power of n. And that's why those are called sequences with exponential growth. I threw in the powers of 4 here because these, of course, in recent years have come up a lot in genomics. When you look at the number of DNA sequences of length n, that's 4 to the n. It grows exponentially, and the fact that it grows exponentially is what makes our genome so powerful in transmitting a huge amount of information with just a small length. So exponential growth is exhibited by many natural processes, and is the reason that it's exponential and growing so fast is what allows it to be so powerful and able to transmit so much information. Okay, so these are the kinds of sequences that mathematicians study. Of course, a lot of them get much more complicated than these. But what often happens once you start looking at some of these sequences is that you find relations among these sequences, and that's another kind of pattern, patterns of patterns. So sometimes the sequences can be related to each other in surprising ways. And here's an example that I was never taught in school, but when I first learned it, I thought, why doesn't everyone learn this? What happens when you start adding up the odd numbers, say? Okay, so you take one of those sequences, we'll take the odd numbers, and what happens if we start adding them up? So, okay, let's just take the first one, you add that up, you get 1. Okay, now suppose you add the first 2. 1 plus 3 is 4. What happens if you add the first 3 odd numbers? 1 plus 3 plus 5. What do you get? 9. 1 plus 3 plus 5 plus 7. What happens if you add the first n odd numbers? Yeah, the pattern seems to say that you get the nth square number, n squared. How many people have seen that before? Less than half. It's a basic relation between two patterns that everyone knows, and yet it's something that we never learn. Okay, so that's a pattern that you see. But of course, we only verified it for the first 4 cases. How do we know that it actually happens forever? It may have just been a false start. So, a question that really makes, I love using this when I teach students. Why is it true? Why is it true that if you add the first 5 odd numbers, you get 5 squared? When you add the first 7 odd numbers, you get 7 squared. When you add the first n odd numbers, you get n squared. Why is that true? And students come up with 17 different arguments for why it's true after working on it for like an hour. And that exercise really opens the mind because there's so many ways to get to the answer. And that really exhibits something about mathematics that we never learned in school, which is that there are many solutions, possible solutions to a problem. And coming up with particularly creative ones is part of the joy of mathematics. And yet in school we're often just taught, this is the way you should do this problem, follow these steps and do it. This is an example of a problem that's so fundamental, and yet there are probably hundreds of possible ways of looking at this. I'll tell you the way that excited me most when I first saw this problem. So why is this true? Well, you can actually see the answer pictorially. You don't have to write down anything, really. You can just see it in your head, why this is true. A picture can explain it, in a picture that you can just picture in your head. But I'll draw it here. And here's the picture. So what's going on here? You can think of, first of all, you can think of a square number as a square array of dots. The number of dots in a square array of dots is a square number. Right? So if you have an n by n grid of dots, the total number of dots is n squared. Right? So here we have a 6 by 6 array of dots. And that's why the number of dots here is clearly 36, 6 squared. On the other hand, by drawing these red lines here, we're breaking up that 36 into successive odd numbers. Right? So this little bottom left dot, that's just one thing there, and then this next layer has 3, and then this next layer has 5, and this next layer has 7, and you can see each time we add an extra odd number, we get the next square. And so that means that when you add successive odd numbers, you always get square numbers. And so if you do n layers, you'll clearly get an n by n grid of dots, and that's why the sum of the first n odd numbers is always n squared. And this is something, once you see this, you'll never forget it. Now you always know, not just that the sum of the first n odd numbers is n squared, but you immediately know why. Just this picture is all you need. Is anyone clear on that? So there are many such relations among numbers that you can just see by visualizing it. People often ask number theorists, you must be scribbling all day. Well, actually, number theorists are usually just thinking in their mind and picturing things for much of the time. And this is like the simplest example of that. Okay, so think about that, and I'll give you, this is often called the proof without words. This is a proof of the theorem that 1 plus 2 plus dot 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 plus 2n minus 1 is n squared. And we didn't have to say any words, just have to draw a picture. That's called a proof without words. Okay, so here's another example of a relation between sequences. I won't tell you the answer for why this time, I'll just show you the pattern, leaving it to you to make the corresponding picture in your head. So what I'm going to do is I'm going to add up all the counting numbers up to a certain point, and then go back down and add those too. So start with 1, okay, it's just 1. And now we can go 1 plus 2, and then back down to 1. Add those up. What do you get? 4. Okay, What happens if you do 1 plus 2 plus 3 plus 2 plus 1? What do you get? Familiar sequence of numbers again. 1 plus 2 plus 3 plus 4 plus 3 plus 2 plus 1. Yeah, that's 3 plus 3 is 6 plus 4 is 10 plus 3 plus 2 plus 1. That's another 6, 16. That's another way of getting the square numbers. So in general, what we're doing is we're adding 1 plus 2 plus 3 all the way up to n, and then coming all the way back down again. Adding all that up. And what is the pattern telling us? What should we get? N squared. Okay, so that's another example of how we just took the counting numbers, we just added up and down, and we're getting the square numbers. Can you find a similar pictorial explanation? So that's something you can think about if you get bored with the rest of my talk. Okay, so that's an exercise for you. There's some numbers that are, once you start to think pictorially, there's some numbers that you can just define pictorially, and some numbers in mathematics are just defined in terms of pictures, not using words. So the hex numbers are best described in terms of pictures. So they're called hex numbers because they come from, well, hexagons arranged in hexagons. So this is sort of the shape of a honeycomb. We start with just one cell. So you can think of yourself as a bee, you made one cell. And now you want to make more cells, so you go all the way around it, and you make your cells in your honeycomb. And then once that's done, you go around again, and you make all the cells and cover all those up. And this is actually how when you sometimes you see honeycombs develop, as they start out from a central cell and start to grow. And so this is the first iteration, and in the second iteration you do all the cells around it. The third iteration you do all the cells around that, and then you do all the cells around that. The fifth iteration you do all the cells around the previous one. And the nth hex number is just defined as the total number of cells you get after the nth iteration. Okay. So here we start off with one cell, then we do 6 around it. That's just as in a honeycomb, we get 7. Then we do 12 more around that, and we got 19. And so on. So then you find you get 37 in the next iteration, then you build all your cells around that, and you find you get 61. So you get this natural sequence of numbers, 1, 7, 19, 37, 61. Something that doesn't have an obvious pattern, right, in terms of, when we were saying square numbers and cube numbers. This one doesn't have an obvious pattern in terms of a formula, that the nth term is like n squared or something. Although you could work it out. But the easiest way to visualize these numbers is to say, well, it's the number of cells in the nth iteration of making a honeycomb. And these are called the hex numbers. And their definition, the best definition really is to say they're the number of cells in these bigger and bigger honeycombs. And so just like we did with the odd numbers, we can start to think, well, what happens if we start adding the hex numbers up? Right? So everyone understand what the hex numbers are? Now we can start adding them up, just like we started adding up the odd numbers and getting square numbers. What happens when we start adding up hex numbers? Well, we can start with 1, and we just get 1. Okay, now if we take 1 plus 7, we get 8. 1 plus 7 plus 19, that's 8 plus 19 is 27. So what's the pattern? We're getting cubes. From honeycombs, we're getting cubes by adding up the layers of the honeycomb. So this leads to the natural conjecture that 1 plus 7 plus 19 plus ... plus the nth hex number should give you n cubed. And again, it's fun to try and think, well, why is that true? You can sort of work out the algebra for why it's true, or there's like one picture that you can put in your mind that will make it clear. This one is harder than the previous exercise that I gave you, but again, if you were already done with that one, I need you to have something in case you get bored for the rest of the talk. Okay. Okay, but this is also one of these beautiful patterns that you can understand both algebraically, and again, I give this to students as follow-ups after the 1 plus 2 plus 3 plus 4 plus 3 plus 2 plus 1. You go to this, and you have to start thinking in 3 dimensions a little bit. The picture will be a little bit 3-dimensional. I want to tell you about the most beloved sequence for number theorists. You can guess what that is. The following sequence is perhaps the one that's studied the most by number theorists. It starts with 2, 3, 5, 7. What's the next one? 11? 13? Not 15? 17? 19? 23? Next one? 29. That's a big jump there. That's right. Yeah, so this sequence is that of the prime numbers. The most widely studied sequence by number theorists by far, I think. So a prime number, if you don't remember from many years ago, it's a number that has exactly two factors. In other words, two numbers that evenly divide it, namely 1 and itself. So like a number like 5, right, 2 doesn't go into 5, 3 doesn't go into 5, 4 doesn't go into 5. Only 1 and right, 5 is just 1 times 5, and that's it. And so 5 is prime. Whereas 6 you can write as 2 times 3. You can break it up into things that are not 1 or itself. That's why 6 is not prime. So why do number theorists love prime so much? Well, it's because the prime numbers, remember I was saying that number theorists view the whole numbers as our universe. The prime numbers are the atoms of this universe, in the sense that every positive whole number can be decomposed, can be expressed in a unique way as products of prime numbers. So in a unique way. So no matter what number you take, you can decompose it as a product, just expressing it as multiplying together prime numbers in a unique way. And every positive whole number has that property, and that decomposition is always unique. So for example, if you take 364, right, this is the way that you can decompose it into prime numbers. 364 is 2 times 2 times 7 times 13, right? These are all elements in the prime number sequence. And that's the only way that you can write 364. There's no other combination of prime numbers that you could take and multiply them together to get 364. So every whole number has attached to it a way of putting it together by taking primes and multiplying them together. So prime numbers, with the prime numbers, you can make every other number just by multiplying them together. And that's why the prime numbers are considered the atoms of our universe of the whole numbers. In some sense, if you understand the primes, you understand all the whole numbers in many senses. Despite how much prime numbers have been studied, because they really are the atoms of our universe, each breakthrough about primes always has applications throughout number theory. So they have been studied a tremendous amount over centuries. And as a result, a lot is understood about the primes. A lot is understood about the patterns in the primes. But also a lot is still not understood. I'd probably say most things are not understood. In fact, every time you understand something further, it turns out you realize that you understand less than you did before because it opens up more questions than it answered. So for example, really basic things about the primes are not known. I could tell you lots of things about what is known, but as I said, there are way more things that are not known. For example, are there infinitely many pairs of primes that differ by 2? That's called the twin prime conjecture. That's not known. So here we have 5 and 7 differ by 2, 11 and 13 differ by 2, 17 and 19 differ by 2, 29 and 31 differ by 2. It seems like you get lots of those primes that differ by 2. Are there infinitely many such pairs that differ by 2? We don't know. Another major question about prime numbers is you can see that every once in a while there's a jump of 4, there's a jump of 2, there's a jump of 4, there's a jump of 6. What are all the possible jumps that you could get? Yeah, that's also not understood. How many total primes are there less than n? Right? Or what is the nth prime number? Is there a formula? All those problems are not understood, although there's this famous $1 million question called the Riemann hypothesis, which is as close as we know it to have a formula for the prime numbers, or at least a formula that tells us how many prime numbers there are up to n. Approximations to the Riemann hypothesis are known, but the whole Riemann hypothesis that tells you really precise answer for how many primes there are up to n is not proven, for which there's a $1 million prize by the Clay Institute. Because if that was solved, that would solve many other problems in number theory, because primes are the atoms of this universe. If we understand them, we understand so much more. So prime numbers are really beloved to number theorists for that reason, and we study them a lot. You might be surprised. So prime numbers are the fundamental objects in the world of numbers, But it might come as a surprise that prime numbers also arise in nature. It seems like this is just like a human invention. Let's take the whole numbers and let's decompose them into the atoms of this world. But in fact, these prime numbers that are the atoms of this world of whole numbers actually arise in nature. And this is something that I found really remarkable when I first learned it. Especially because I get to see this in Princeton every 17 years. So I've only seen it once, actually. So this here is a cicada. They live underground for most of their lives. And then every n number of years, so the reproductive cycles happen for different species. They happen at intervals of n years for some values of n. And that value, so cicadas live underground. They emerge only once every n years. Their cycle tends to be n years long, where n tends to be a prime number. And in fact, generally 13 or 17. In Princeton, there are two species. One comes out every 13 years, one comes out every 17 years. So why do they do that? And how do they know about prime numbers? So, well, the answer is, so the hypothesis is that if n is a prime number, and so n is the length of their cycle, then that n is least likely, right? If it's prime, it's least likely to be a multiple of the cycle length of its predators, right? So, for example, if the cicadas decided to come out every 12 years, and there was a population cycle of predators that happened every 6 years, or even every 4 years, or every 3 years, or every 2 years, right? It could coincide with the cycle of the cicadas, because the cicadas are happening every 12 years. So even if the predator's motion was going up and down in a cycle, if it peaked at the same time every time as when the cicadas came out, the cicadas would die off. And in fact, that's probably what happened to the 12-year cicadas, which is why we don't see them anymore. So how did cicadas discover prime numbers? Well, by living, the ones that discovered prime numbers lived, and the other ones probably didn't, unfortunately. And this is often how nature beats us many times to the discovery of fundamental kinds of numbers through the process of evolution. Darwin wrote extensively about various cycle lengths in his Origin of Species, and described how evolution would allow species to find the optimize various mathematical functions that we humans are still struggling to do, and they discovered by billions of years of evolution. And that's why often we're able to take nature, look at the patterns in nature, and ask, what is the optimization problem that this evolutionary process solved? And then we as mathematicians can go and try and understand it on our own. So that's why nature has been a great source of inspiration for outstanding mathematics and mathematical structures. So yeah, that's an example of how prime numbers arise in nature. I should mention that prime numbers also, they don't just arise for cicadas, but they also arise every day for humans, not just mathematicians. So in modern times, prime numbers play a role in our lives every day due to the following fact. Suppose you have a 200-digit prime number. And it turns out it's not so hard to produce 200-digit prime numbers because they're easy tests. You just write down a random 200-digit number, and there are quick tests known to decide whether they're prime. So you just take a few random 200-digit numbers and then throw them out if they're not prime, and eventually you'll have two 200-digit numbers that are prime. That's very quick to do on a computer. And so say you have two 200-digit prime numbers, and you give them to your computer, and you ask your computer to multiply them. Your computer will be able to multiply them together in a fraction of a second and give you the resulting 400-digit answer. Okay, so that's something that computers can do very fast. Multiply two 200-digit numbers to give you the 400-digit answer, fraction of a second. But now suppose you take this resulting 400-digit answer and give it to another computer and ask it to do the reverse process, find those original two 200-digit parts. The best known algorithms working on all the world's computers simultaneously, you shouldn't give it to the computer you had originally used because it would probably know. But if you use all the other computers in the world, and put the best known algorithms on them and have it work for billions of years, they would still not be able to find those 2 prime numbers. It's very counterintuitive. So it's very easy. We know how, computer algorithms know how to multiply 2 200-digit numbers very quickly, in a fraction of a second. But that reverse process, our best known algorithms working on every computer in the world for billions of years, does not know how to do the reverse process. So we don't know how to do that reverse process. And because we don't know how to do that reverse process, we take advantage of that. Often, in mathematics you usually hear that somebody solved the problem and therefore it has this application. In this case, the situation is that no one has solved this problem, and that's why we have an application. Because people have tried for decades, and no one's succeeded, and so everyone thinks, okay, it's probably hard. And so let's use it for our daily security. So the fact that it's easy to multiply 2 prime numbers together, but hard to do the reverse process, that's the basis of much of the world's encryption schemes. So when you submit private information, for example, your credit card number on the internet, those numbers are encrypted before they're sent. And if a hacker was to intercept it, he would see this encoded message. He should not be able to decode it. And what we assume is that hacker does not know how to do that process of taking a 400-digit number and breaking it up into 2 200-digit parts. That's what we're assuming every day when we submit our credit card number on the internet. So that encryption process uses the product of those 2 200-digit numbers in a way that the only way you could decode it is if you could break that 400-digit number into its 2 200-digit parts, and that we think no one knows how to do. So since no one knows how to factor numbers, or so we think, we don't know that for sure, this method of encryption is presumably secure. It's a little dodgy because it's certainly possible that somebody in some tank somewhere knows how to do it and is reading everything that we send every day. There's no reason that that's not happening, actually. And that's why, this is exactly the reason why Dick was mentioning how number theory is an art. Well, number theorists work on prime numbers because of the artistic aspects of it. But one of the reasons that number theory has become one of the most heavily funded branches of mathematics is because of this problem. Our world security relies on somebody figuring out whether it really is a hard problem to factor numbers. So one of the fundamental problems in number theory, and it was fundamental even before, it comes up in Gauss's work in the 1800s, he brings up this as one of the most beautiful problems, is to go backwards, do the opposite process of multiplication. But of course it's become not just one of the most fundamental problems in number theory, but also the most important problems in number theory for society, is either to prove that it's difficult to go backwards, right, and break up numbers into their parts, or find a quick way to do it, so that if somebody out there is doing it, we know that they really can be doing it. So if somebody finds a quick way to do that reverse process, taking a 400-digit number and breaking it up into 2 200-digit parts, that would make all these encryption systems that we use, like RSA, is the most famous one, it would make them useless. But in any case, it's important to know which is the case, because our security depends on it. And it's kind of remarkable that we don't have a proof that it's hard to do. We just assume it's hard to do because number theorists haven't been able to do it for decades. Is that a good reason? I don't know. But so far, that's the best we have. But people are always thinking, in case somebody does manage to factor, people are always thinking of the next best encryption schemes to use, based on other mathematics and other hard problems in mathematics. Okay, so that's how prime numbers enter our daily lives. They really our security depends on them on a daily basis. Okay, so here's another place where we were speaking of hex numbers and honeycombs. Another place where mathematics was inspired by nature, by patterns in nature. So the question is, bees build their beehives in these honeycomb shapes. And why do they do that? There must be, again, an evolutionary reason. And in fact, this is the phenomenon that Darwin wrote about very extensively in The Origin of Species. Why do bees use these hexagonal tilings to make their honeycombs. Okay, so why do bees build hives in this hexagonal pattern? And, well, the evolutionary hypothesis here was actually conjectured. It's called the honeycomb conjecture back in 36 BC by a Roman writer and agriculturalist. So he was looking at these beehives everywhere. Every community of bees was using the same pattern. And so what he hypothesized, the reason that they must be doing this, is this following honeycomb conjecture that he made in 36 BC, which says that if you take any division of the plane, because the plane just means flat space, so their honeycombs are flat, made up of cells of certain shapes. They have to build the walls of those shells. And they want to divide the plane into regions of equal area, okay, by building those walls. Okay. So you can think, if humans ever wanted to do that on Earth, they wanted to divide it into cells of equal size. Fortunately, humans don't do that. But if they did, then they'd want to build fences, and they'd want to divide the land into little pockets of equal area so that the least amount is used. Right? And for the bees, they're dividing their honeycomb into cells, each of the same area, so that the least amount of wall needs to be made. So the honeycomb conjecture in the technical language that he was already writing at the time, in 36 BC, said any division of the plane into regions of equal area will have perimeter, at least that of the regular hexagonal honeycomb tiling. Okay. So if bees did anything else, they would strictly be building more walls to get the same areas for their regions. So in other words, the hexagonal tiling optimizes the amount of hive you have to make to get equal pockets of a given area in your honeycomb. Does that make sense? So Darwin writes about this. This must be the case because bees have to compete with each other for the resources that they have. If they're spending all their time building walls in their hive, they're probably not going to survive against the ones who were building it in the hexagonal tiling because they had to spend less time making those walls. So that's why the bees that were doing it with the optimum amount, the least amount of wall building, were managing to get the most honey and were the most likely to survive. So this argument of Darwin is very convincing that this fact must be true, this honeycomb conjecture must be true, because otherwise other bees that were building in other shapes would have been the ones that were winning. So this was a conjecture, this was a conjecture that was considered by mathematicians for, the next 2 millennia to actually prove this. Not prove it using evolution, but proving using mathematics. And amazingly, this was proven only very recently, in 2001, by Tom Hales. So I love this problem because it's a problem that illustrates its origins go back over 2,000 years, and it took 2,000 years to solve this problem. There were lots of techniques developed for this problem. The whole theory of lattices and lots of number theory goes into this. And the proof finally came together in 2001 by Tom Hales, a mathematician at Pittsburgh. And you can imagine that this fact has many applications throughout science and engineering, right? Knowing how to divide regions into pockets of equal size, where you have to build the least amount. So telescope mirror structures and nanotubes in recent times. So nanotubes are little hexagonal tubes, and their cross sections are honeycombs. So they transmit equal amounts in each of these tubes, and it requires the least amount of wall to make them. So these hexagonal patterns are, of course, now very, very useful to us in the real world. But they were discovered by bees. Literally. One other kind of sort of packing problem that was really my favorite problem when I was a child. This was sort of the first math problem that I ever worked on, so I thought I'd share it with you, which was about stacking oranges. When you go to the supermarket, you often find that oranges are stacked in these pyramid structures. So this is a pyramid, triangular pyramid, right, where there's sort of 4 oranges on each side. Usually they're bigger, but we usually didn't buy the whole stack when we went to the grocery store. And this is about how many I could convince my family to buy so that I could make my own pyramids. And the question, so I enjoyed, as I said, I enjoyed making these pyramids at home. I was about 7 or 8 years old, so it was one of my pastimes. And my question was, well, how many oranges? This is the sort of the first math problem that I ever tried to solve myself, sort of posed and tried to solve. How many oranges are needed to make a pyramid stack having n oranges on each side? So, for example, this one there has 4 oranges on each side. And does anyone see how many oranges were needed to make that? Any guesses, approximately? 20, that's right. Yeah, there are 20 oranges in there. So to make a pyramid with 4 oranges on each side, you need a total of 20 oranges. So if you want to make a pyramid with just 1 orange on each side, okay, how many do you need there? 1. Okay, how about with 2 oranges on each side? 4. Okay, how about with 3 oranges on each side? So how many will that bottom layer have, is the question. Oh, we'll have like 1, then 2, then 3. You can sort of imagine there are going to be 6. There are 10. And then as everyone said, for 4 oranges on each side is 20. And then it goes up like this. I never quite actually made the pyramids of size 120. But eventually you start to visualize it. And so I worked out the sequence and I asked, well, what is the formula for the nth term? Is there a formula for the nth term? Right, so how many oranges do you need with n oranges on each side? And yeah, this moment for me when I figured out the answer was something that I still remember, because it's sort of the first math problem that I remember solving. And so I'm going to, spoiler coming in case you want to solve it on your own. I'm just going to tell you the answer so that you can. So the answer is n times n plus 1 times n plus 2 divided by 6. And finding that answer was a real inspirational moment for me because, well, first of all, the solution, why that's true. And I urge so this is also a problem I still give to students as one of the next ones in trying to visualize and understanding why patterns hold. So why does this formula hold? There are many, many solutions for why that's true. So that was the first part of what I found inspirational, is the process of arriving at an answer. But the other part of this was how much it dawned on me the power of mathematics, the predictive power of mathematics, that now, if I want to know how many oranges I need to make a pyramid with 10 oranges on each side, I don't have to build the pyramid. And I don't have to convince the family to buy that many oranges. I can just plug it into this formula, and it predicts how many you would need if you had to make such a... So if you plug in 10 in here, you do 10 times 11 times 12 divided by 6. And that gives you the answer. And so it really shows the predictive and the power of mathematics. Especially in school, if I feel like I was lucky that I stumbled on this problem, and I had a mother who was a mathematician who didn't think I was crazy when I asked these such questions. And if we had that more in school, that students could pose their own questions and come at answers from many different ways to use creativity and then enjoy the predictive power of mathematics in this way, I think it would inspire many students as it did me. Okay, so we talked about the most beloved, most important sequence in the nature of numbers, whole numbers, the prime numbers. But perhaps the most common sequence that actually occurs in nature, more than the primes, is the following sequence. So it starts 1, 2, 3. You can't judge the pattern too soon. 5, 8, 13. Next one. 21. 34. That's right. So, as Dick mentioned, my grandfather was a Sanskrit scholar, and I used to learn Sanskrit from him. And I actually learned these numbers from him. He wasn't a mathematician. And so, actually, among Sanskrit knowers, these are called the Virahanka sequence. Virahanka numbers. In India, there's now some of the books are changing to Virahanka Fibonacci numbers. They've been Fibonacci numbers in India until now, with the colonial textbooks. So Virahanka lived around the year 700. And so he described the sequence. He said, write down the numbers 1 and 2. And then each subsequent number you write down is the sum of the previous 2 that you wrote down. Right? So we wrote down 1 and 2, and then 1 plus 2 is 3, 2 plus 3 is 5, then 3 plus 5 is 8, and then 5 and 8 were the last ones you wrote down. You add and you write down 13, 8 plus 13 is 21, and so on. 13 plus 21 is 34. So that's the procedure that Virahanka wrote down in a linguistics textbook back in the year 700, 500 years before Fibonacci. So he was a linguist, which is part of the reason why even today in India, lots of mathematicians are unaware of his brilliant mathematical work. So I first learned of these numbers from my linguist grandfather. I actually learned them as the Hemachandra numbers, named after another linguist who lived about 50 years before Fibonacci, and whose works were much more widely disseminated at the time, because he was also a great Jain philosopher. And so Hemachandra was known for his great philosophical works, and in those philosophical works he also discussed these numbers from a linguistic point of view. These numbers were also written about by another linguist in the year 1135, known as Gopala. I had a chance to become familiar with the work of Hemachandra, which is how I learned about these numbers. And the question that mathematicians always ask when they hear, well, these numbers first came up in the context of poetry and linguistics. Well, why were these Sanskrit linguists interested in these numbers? It was for a really beautiful reason. So as I said, these numbers are known in the West as the Fibonacci numbers, after Fibonacci, who lived after all these authors who extensively discussed these numbers before him. Okay, so why do these numbers come up for linguists? These numbers first came up for humans in the context of poetry. And I find that an amazing story, because it really illustrates the fine line between art and mathematics. These people were poets. Hemachandra, Gopala, and Virahanka, the very first, were fantastic poets. And yet, they were writing extensively about these numbers. And that really shows the fine line between art and mathematics. And again, this is one of the stories that I was lucky to grow up with that also really inspired me and showed me the relation between art and mathematics. So let me tell you how these numbers arise in poetry. So here's a little background on Sanskrit poetry. So in Sanskrit poetry, there are two kinds of syllables. So just like in many languages, there's a notion of stressed and unstressed. In Sanskrit, there's a notion of stressed and unstressed, but it goes further than that. Stressed syllables are called long, and unstressed syllables are called short. And the reason for that is that long syllables actually take longer to pronounce than short syllables. And not just slightly longer, they're exactly twice as long. So short syllables you can think of as taking 1 beat of time to say. Long syllables take 2 beats of time to say. And you can imagine, once you have that set up, there are all sorts of mathematical questions that arise. If a long syllable takes 2 beats of time, a short syllable takes 1 beat of time. Okay, so long syllable lasts 2 beats. Short syllable lasts 1 beat when you pronounce set syllables. That's how Sanskrit poetry is read. And so that simple setup of the Sanskrit language, and there are all sorts of quirks about the Sanskrit language that make it very mathematical. The alphabet is arranged in a 5 by 13 table. There are 2 coordinates. It's that every sound you specify the 2 coordinates, and that specifies the sound. Somehow these ancient linguists were artists and mathematicians simultaneously in developing the language. And the way it evolved, it sort of evolved through very artistic and mathematical thinking. And another one of the things that turned me on to mathematics was the study of this kind of linguistics. So this is just one example. The way poetry is read, you have long syllables and short syllables. Long syllables take 2 beats of time. Short syllables last 1 beat of time. And this leads to numerous mathematical questions which the ancient poets considered in great detail when they were writing their poetry. And they would also write poetry about these problems and their solutions in poetry. Okay, so long lasts 2 beats, short lasts 1 beat, and you can ask how many rhythms, right, how many poetic meters, is the way they said it, can one construct of, say, 8 beats, right, consisting of long and short syllables. Right, so if you have 8 beats of time, and you want to fill it with long and short syllables, long takes 2 beats, a short takes 1 beat, how many ways can you fill in those 8 beats? Well, you could go long, 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 long. Or you could go short, 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 short. Or you could go short, long, long, short, long. Long, long, short, short, long. I read a lot of Sanskrit poetry, so these things are... I've had a lot of practice with this. Okay. So these are 4 examples of rhythms, right, that are made of longs and shorts that take 8 beats. How many total are there, was the question that was posed actually by a linguist. It seems even as far back as 500 BC by a linguist named Pingala. But it was first solved in poetry in around the year 700 by Virahanka. So they thought of it in this more mathematical language as well. And how many ways can one write a number n as a sum of 1s and 2s? Right? That's an equivalent question. We're asking how many ways can we write 8 as a sum of 1s and 2s? We can write it 2 plus 2 plus 2 plus 2, or we could write it 1 plus 1 plus 1 plus 1 plus 1. And so, right? So the way to get started on any such question, just like all the other number sequences we were talking about before, is to try the first few examples. So n equals 1. Okay, if you just have 1 beat of time, how many ways can you fill it with longs and shorts? Well, just 1, because there's no room for a long. Okay, so just 1 way. Okay, but if you have 2 beats, what can you do? You can do short, short, or you can do long. Okay, so you can do short, short, or long. So there are 2 ways. For n equals 3, you can do short, short, short. You can do short, long. You can do long, short. Oh, I said that backwards. Doesn't matter. There are 3 total ways. Okay, and then for n equals 4, again, you can work out all the possibilities. It turns out there are 5 ways to do it. Yeah. Okay, and then you start to see, here are the 8 ways to break up 5 beats into longs and shorts. Starting with short, 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 and then long, short, 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 and so on. So 8 ways. And so that's the sequence that was observed. And so, it's the sequence where each element looks like it's the sum of the previous 2. And so, to answer the question of how many rhythms, how many poetic meters are there with 8 consisting of longs and shorts, you just keep adding the previous 2 until you get to the 8th number, and that's 34. And so 34 is the number of poetic meters having 8 beats. It's the number of rhythms having 8 beats with longs and shorts. Okay, so that's the pattern observed. But these linguists went further than that. As I said, mathematics is not just about finding the patterns, but it's about understanding why those patterns are true. Why is that true in this case, that the total number of rhythms having 8 beats is the sum of the number of rhythms having 7 beats plus the sum of the number of rhythms having 6 beats? Why is that true, that the answer is always achieved by adding the previous 2 elements in the sequence? And they give a beautiful... So in these works by Virahanka and Gopala and Hemachandra, they give a beautiful argument for why that's true in poetry. The poems are very short. Their argument, this is the entire argument. The argument is, if you have an n-beat rhythm, it ends in either a short or a long. Therefore, this method works. Okay, so you have to unravel that a little bit, but that's really all you need to say, and let me explain why. So if you let Vn, okay, be the nth element in the sequence, and so that Vn be the number of n-beat rhythms, okay, of longs and shorts. Okay, well, their argument is that every n-beat rhythm ends in either a short or a long. Okay, so let's take all n-beat rhythms and break them up into those that end in short and those that end in long. How many n-beat rhythms end in a short? Well, if you take the short away, what do you have left? An n minus 1 beat rhythm. How many of those are there? Vn minus 1. Okay, now you take all the n-beat rhythms that end in a long. How many of those are there? Well, if you take away that long, what's left? An n minus 2 beat rhythm, of which there are Vn minus 2. So the point is that you can make all n beat rhythms, right, by taking all n minus 2 beat rhythms and throwing on a long at the end, or taking all n minus 1 beat rhythms and throwing on a short at the end. And therefore, Vn is equal to Vn minus 1 plus Vn minus 2. In other words, each element in the sequence is the sum of the previous two. And that's this very elegant argument given in poetry in the year, at least as far back as 700, and maybe earlier. So this is a story that really inspired me when my grandfather told me about it. Because these numbers, which are so fundamental in mathematics and science, first arose by the work of artists, poets who actually cared about the meanings of these numbers in terms of how many ways they could construct poetic meters. Of course, now the Virhanka Fibonacci numbers arise all over mathematics and all over art. So, of course, their origin is in poetry, but of course, we use it a lot in drumming as well. Many times in music, you have this dichotomy between longs and shorts, and you're improvising, and you need to know, if you have 8 beats of time left, how many ways can you fill it in? You don't even just need to know how many ways you can fill it in. If you're on stage improvising, you need to know what those ways are and be able to draw from it in an artistic way. But first, the first ingredient is to know what the repertoire is. There are 34 possibilities, and then you need to draw from it on stage according to the artistic mood of that moment. These numbers are used a lot in the visual arts. I'll show you some examples later, perhaps. Modern architects use them a lot. But my favorite place where they arise, as I said, lots of times humans discovered these fundamental mathematics objects, but of course nature had discovered them long ago through evolution. And the same is true here. In nature's art, you find these numbers all over the place. Too many to describe in one lecture, but I'll show you a few pictures. Daisies, if you count the number of petals on daisies, they tend to be one of these numbers. So here, this is a daisy with 13 petals. And this here is a daisy with 21 petals. I counted, don't worry. And if you really think these are just coincidences, this is one of my favorite pictures. There's a whole garden of daisies, and each one of these daisies has 34 petals. Again, I counted them, just to make sure. Now, wherever you can see there are 34. Each one of these daisies has 34 petals. And so this is something that you can really observe. You look at different species of daisies, and they all, there's some that even have 89 petals. There are species that have 89 petals, and some have 55 petals. So that's really a thing. They really discovered these numbers. And the question is why? And that's always the question. Well, why were they trying to get this number of petals? And it took a long time to really understand why that's true. It's sort of understood now. And I'll get to it in a second, why that happens. It doesn't just happen in flowers, but it also happens in pine cones and pineapples, anything that has this kind of spiral growth. So these have sort of spiral growth of seeds in the center. So these sunflowers have seeds that grow in the center which sprout these petals, and they grow in a spiral. In the same way, these pine cones, these cells in the pine cones grow in cells, in spirals. And if you count the number of spirals, you see there are 13 spirals. And you can really do this. You pick up a pine cone and you count the number of spirals. You'll always tend to get one of these numbers. And you can count in either direction. You can count the spirals going counterclockwise in this case. You could also count them going clockwise. How many clockwise spirals do you think we'll get? I don't expect you to count that quickly, but it really helps to do it. I've done this a lot. Yeah, 8. Very good. Here we go. The number of clockwise spirals are 8. So 13 going in one way, 8 going in the other. And that's typical of what happens in pine cones. If you count them one way and count them the other way, they're consecutive Virhanka Fibonacci numbers. And if you really want to try this, I've had to do this a lot in the classes I teach. It helps to have a marker, a permanent marker, so that you can, because otherwise you lose track as you're rotating it. One of the things I do in my class, you can go to pinecones.com, turns out, and you can buy pine cones in bulk. And I actually did this. I bought bulk of pine cones, and there were about 200-300 people in the class. They each get a pine cone. And one of their homework assignments is to count the spirals. And over 90-something% get consecutive Virahanka Fibonacci numbers. And the other ones I say, oh, well, something must have fallen off. Or you did it wrong. I try not to say that too much. Okay, one other property of the Fibonacci numbers, or the Virahanka numbers, is that if you take consecutive ratios, right? So remember, in these pine cones, we were seeing these consecutive Fibonacci numbers. What happens if you take successive ratios? So in other words, you take 13 over 8 in this case. But in general, let's take ratios of successive Virahanka Fibonacci numbers. So you start with 2 over 1, then 3 over 2, then 5 over 3, then 8 over 5, then 13 over 5, then 21 over 13, and so on. It turns out, so try this on a calculator, and see what you're getting numerically on your calculator. It turns out that as you go further and further along in these ratios of successive Virahanka numbers, you get closer and closer to one single number, which will look like 1.618 ... And that you can mathematically prove, and that's also a fun thing to work out. If you've never seen that before, is the number that you get closer and closer to is 1 plus the square root of 5 divided by 2, which numerically is about 1.618. And this has been called by mathematicians for ages the golden ratio, or the divine proportion. There are many tall legends about all the superpowers that this number has. The divine proportion. It has divine properties. It has all sorts of superpowers, many of which are actually true. But of course there are lots and lots of legends about it and their divine properties which are, well, not quite so based in science. So I won't talk about those as much. But there are many amazing properties of this number that actually are true. And if you're mathematicians, probably every mathematician has encountered the golden ratio in their work sometime or other. They appear everywhere in mathematics and in nature. So the golden ratio plays a very important role throughout mathematics, in the theory of tilings and partitions and continued fractions, Afantian approximation, all kinds of geometry, entropy, and more. It really is ubiquitous. But it also plays numerous roles in nature. Sometimes more things are ascribed to the golden ratio than are scientifically proven or understood. But there are many that have been sort of scientifically understood. A primary example, one of the oldest in nature that humans understand, is in the area of what's called phyllotaxis, which is the study of the arrangement of leaves on a stem. So when a stem grows, say, of a sunflower, so the stem grows, it sprouts leaves in a spiral pattern. So it doesn't always sprout a leaf on the same side. The reason is that, well, all the leaves want sunlight. So that's why plants like to sprout leaves in a spiral pattern, so that each one comes out at a different angle, and that maximizes the sunlight coming to those leaves. And so here's a top view of a plant that's been sprouting leaves from its stalk, from its stem. So everyone understand the stem is sort of coming out at you, and these leaves are coming out in spirals around that stalk. And I've put little numbers there that indicate which one was sprouted when. So you can see here that this was the first leaf that was sprouted, and this is the second one. And the amount of turn is a certain angle. And then if you go from 2 to 3, it's another angle. And if you go from, say, 5 to 6, it's this other angle, which is in white. So between 1 and 2, there's that black angle, right? And then between 5 and 6, there's that white angle. And they're the same angle. In fact, all these plants, they decide what angle they're going to turn at before sprouting a leaf. And they all do that consistently. And this plant has chosen this angle. In fact, many, many plants have chosen this angle. This angle is what's called the golden angle, 360 degrees divided by the golden ratio. I mentioned this area of mathematics called Diophantine approximation here. It used to seem like just a technical area of number theory. You want to understand how well irrational numbers can be approximated by rational numbers. Turns out the golden ratio is the hardest number to approximate by rational numbers. And plants love that. Don't we all? Because it's the hardest number to approximate by rational numbers, if it's sprouting plants at the golden angle each time, it's not going to coincide with itself. It's going to sort of maximize the chance that it doesn't coincide with itself. Right? So if you go with the first n rotations, because it's the hardest to approximate with rational numbers, it doesn't come onto itself. So example, if you rotated by, say, a half turn, right? So for the first time you do it, that leaf is happy. But when the second one comes around and it's just a half turn and comes out again, it's underneath the previous one. So half turns are no good, and the same reason third turns are no good. 2/3 turns are no good, because after 3 you start to repeat. But if you do golden angle turns, that sort of stays away from repeating the most, because it's the hardest number to approximate by a rational number. And that's why plants love the golden angle. And that's actually related to why daisies had Virhanka Fibonacci numbers of petals, is that they were sprouting petals from a spiral growth of seeds inside the head of the flower, and the tightest packing that it could manage is by the golden angle. And then when things happen in the golden angle, the best rational approximations to it are exactly these successive ratios of the Virhanka Fibonacci numbers. Okay, so there's a lot of mathematics actually that goes into understanding this, but plants had discovered this way before, just through evolution. Which again I find very inspirational. It's very useful sometimes to look at nature to understand the true mathematics of what's going on just in our world of numbers. Okay, when I was thinking about these cyclic symmetries, I was reminded of this one other favorite number that I had. It's still one of my favorite numbers, 142,857. How many people have seen that number before? Yeah, a few. It's a very special number, and here's why. So if you take 142,857, if you multiply it by 1, you get 142,857. Okay, that wasn't as surprising as the next one. If you multiply it by 2, look what you get. You get 285,714. Are you impressed? Okay, you'll be impressed with this number soon, I promise. If you multiply it by 3, what happens? You get 428,571. If you multiply it by 4, you get 571,428. If you multiply it by 5, you get that. If you multiply it by 6, you get that. What happened? As you multiplied by 1, 2, 3, 4, 5, and 6, all that happened to the number just cycled around in the 6 possible ways that it could. You multiplied by 1, 2, 3, 4, 5, or 6, and it just cycled around in the 6 possible ways that it could. For that reason, this number is called a cyclic number, because its first several multiples just cycle the number in all possible ways. Where does this number come from? I'll give you a hint. If you type 1/7 in your calculator, and you should look at what number you get, and that'll give you a hint of how this number was discovered. Okay, so type 1/7 in your calculator. Just remember that. The question is about cyclic numbers is, are there other such numbers? Are there other such n-digit numbers? Right, this was a 6-digit number, but are there other such n-digit numbers? So that if you multiply by 1 through n, you just get all the cyclic arrangements of that same number, just like happened with 142,857. So, digit numbers, so that if you multiply by 1 through n, the number just cycles around in all the n possible ways. The answer is yes, there are other such numbers. I'll give you one more example. Here's a 16-digit number. I don't expect you to remember this, but if you want to remember it, just think about typing in 1/17 in your calculator. Instead of 1/7, if you type 1/17, you get this you'll find that the first 16 digits are these 16 digits. And this number, again, has the property that if you multiply by the numbers 1 through 16, this number just cycles around in all 16 possible ways. So it's quite a beautiful thing. Sometimes magicians love these numbers. You can use them for amazing predictive tricks, including card tricks. The question is, one of the questions that's sort of become one of the fundamental questions in number theory. People don't phrase it in this recreational way, but the question is, are there infinitely many such numbers? So can you have arbitrarily large n-digit numbers so that if you multiply by 1 through n, the number just cycles around? And this is an unsolved problem. Nobody knows the answer, but it actually, even though it seems so recreational, it actually lies at the heart of many fundamental questions in number theory. It's what's called Artin's primitive root conjecture. And if Artin's primitive root conjecture was true, then that would imply there are infinitely many such numbers. And that's what's expected, is that there are infinitely many such numbers. And in practice, you can find them. People have found many. But the question is, can you have arbitrarily large ones? And that's an unsolved problem and lies at the heart of a number of important problems in number theory related to Artin's conjecture. But I love this example because I sort of encountered it learning magic early on. I encountered it in that context, and then later on when I went into number theory, I learned this thing called Artin's conjecture, and this connection was something that I found very, very fascinating and very inspirational. So the fact that these patterns in different areas came together like that is, again, one of those moments that you love as a scientist. Okay, so I'll end with one last instance of how nature has inspired mathematics. You've all seen self-similar fractals. So a self-similar object, or fractal, is one that exhibits the same shape as itself at smaller and smaller scales. So you keep zooming in, and you keep seeing it over and over again, the same object. That's what a fractal is. So one of the most beautiful examples of a fractal is the fern. So the fern is a plant that looks like that. And so you can see that you go up on the stem and you have all these leaves sprouting out from the stem. And look at the leaves that sprout out of that stem. They look like itself. And if you look at the leaves that are the sub-leaves of those leaves that are sprouting out, they also look like just itself, just smaller and smaller versions. So that's what self-similarity means, that you keep zooming in. Imagine if I had just shown you this picture and just made it bigger. It would have looked exactly the same as this picture. Except it happens not to be coming out of the ground. But other than that. And the same thing, if you took one of the sub-leaves there and made that big, it would look exactly the same as this picture. You wouldn't be able to tell. That's what a fractal is, or a self-similar object is. And there are so many in nature. And the fern is a fundamental example that's often used as the first example in any class on fractals. But similar phenomena occur in snowflakes. Often you'll see a six-sided snowflake, and if you look at the snowflake, any one of the six strands that's coming out of the center, and it has little leaves again, and you look at those, and it looks exactly like that first leaf that came out, and so on. So there's lots of self-similarity in snowflakes, in leaves, as we've seen, in clouds, in coastlines. You look at the shape of a coastline, and then you zoom in. Well, there's just so much. There's infinite detail in the coastline. You look at it again, it just looks like kind of similar to what it did before you zoomed in. That happens in coastlines and mountains. Lightning, if you've ever seen lightning sprout, it often sprouts in a fractal-like pattern, where each of the sub-sprouts look like the original sprout, because it has so much infinite detail in it. So the fractal behavior of nature is one of the things that really inspired mathematicians to look closely at fractals. In particular, Mandelbrot, who was mentioned in our symposium today, took these ideas very, very far. But fractals existed in man-made art even before the subject started formally. This is a temple in Madhya Pradesh in India. So I used to visit India when I was young, and this is a picture that made me think, oh my gosh, how if you go to this temple and you sort of zoom in and look closely at one of these, say, just look at this area of the temple right here, it looks like it was deliberately made to be a copy of that whole big temple. That much detail is in that little thing, even though you can't see it here. And then in those little things, there are other sub-things, and those look also just like the original temple. So these kinds of ideas of art, fractal geometry and art, arose in all sorts of architecture, even in ancient times. This is an example from India. There are lots of examples of fractals in art from Africa. This is an example of a Fulani wedding blanket from Nigeria, made in an ancient tradition. And the idea is that it's a pattern of diamonds, and inside those diamonds are diamonds, and if you look up close, you'll see that those diamonds have those same patterns of diamonds inside. To remarkably so, this is not a high enough resolution for you to really see these diamonds in here, but many iterations of that are done and those smallest iterations require the most amount of time, but are also considered the most important in the tradition. That's where these are used in weddings, and the good energy the really high energy stuff happens at the nth iteration, at the fourth or fifth iteration. That requires just tremendous amount of detail to make. Of course, there are modern examples where fractals are used in art. Escher was a famous example of making beautiful fractal art. If you stare at this long enough, you'll start to look inside. You'll see copies of the whole thing inside. And it takes a while to be able to see that, but I'll show you the shading so that you can see. I showed you two. I've shaded one in light, the big one, and then inside it's shaded a little darker. And if you look at it, it's exactly the same. And that was Escher's point, smaller and smaller. Same thing, just smaller and smaller in the same picture. So we learned these ideas from nature, but they've been used by humans to make really beautiful art. So there are patterns all around us. I want to end with an example that just happened a few months ago. Sometimes in Princeton I go to a co-op called 2D. And this is a picture that was taken by members of that co-op. It's a fractal broccoli. And they kept it there on the table for days because they couldn't get themselves to slice and dice it because it had such perfect fractal pattern. If you look at any one of these horns on the broccoli, they're exactly a copy of the broccoli. Right? And then those horns have little tiny horns, and those also look like a copy of the whole big broccoli, and so on. It's a fractal broccoli. It's called Romanesco broccoli. It often grows in perfect fractal patterns. And for someone who teaches mathematics at Princeton, this is like the most best moment that you can see from students there. Because this broccoli had an obvious application, namely dinner. And yet, they took a step back to admire the art of it and the science of it. And they kept it there for days, and didn't use it for that particular application. Instead, hundreds of students got to see it lying on the table, and there were discussions about fractals all week because of that, and people learned about fractals and about fractal art all week. And that, in some sense, was a better application in the long term for that broccoli. So that's what I want to encourage everyone to do. Patterns occur all around us. You have to discover them, understand them, and that makes our life richer, and it leads to applications that you could never have fathomed before you realized those things were there. So I encourage you all to find the patterns and beauty in your lives, because they definitely exist. Thank you so much. I'll stop there. Thank you so much.
Fascinating, wonderful. I don't know that we can thank Manjul enough for this evening. I'm sure that you have increasing sequences of questions that you'd like to ask. But I'd like to suggest that there's a reception afterwards, and this would be a good opportunity to chat a little bit informally and among yourselves as well. Let's thank Professor Bhargava again for this.
Thank you so much. Thank you. Thanks so much.